Okay, so first of all, what's your name?
My name is Joan.
Joan
Feldman.
Feldman. F-E-L-D-M-A-N?
Right.
Okay, and what is your profession, or like what do you do? Or
Well, right now I'm a real estate agent.
okay.
But I've had a number of professions.
And what are your dogs' names?
This is Dante and this is Molly.
Nice.
And Molly is a collie.
So I'm doing my film about mathematics and where math comes from and what it should or can be used for. And I'm wondering what it's going to be a video essay. I'm going around and interviewing absolutely everybody, and I'm going to edit it together about math to try and explore mathematics. Like, where do you think math comes from? Is it created, or do we discover it because it's already here? It's definitely already.
Yeah. Relationship. Mathematics is relationships. Relationships always exist.
Mathematics is one of the most vital disciplines that one could possibly study.
I think it's the most satisfying possible academic discipline.
I think it's really fascinating.
Yeah.
About the ways how it's advancing.
As odd as it may seem, one of the things I like about math is the fact that so many people hate it and are afraid of it.
Que es muy difícil.
Very difficult.
Hay que tener mucha práctica.
A lot of practice.
What society perceives math to be and what math is, I think, are two very different things.
I haven't used
But
like I'm thinking about my high school math classes, and I haven't thought about like tangent, cosine since then. So like I feel like those type of things aren't relatable.
My non-math friends find it hilarious that if I tell them, I go out to dinner with, a bunch of mathematicians, the bill comes and, we're splitting it evenly three ways, and we can't even do that.
I'm sure they have some kind of,
value.
For scientists that use math, I mean, just because you didn't use it at like the video store doesn't mean that.
Okay, yeah. That's true.
Perhaps more the phenomenon that you're speaking to is that, it's this using numbers somehow is more convincing to people, because they think that all this hard math went in behind it.
For example, real estate. The mean price because there are things that sell way, way high, the mean price may be much higher than the modal price.
Usually, there's lots of math that comes out with numbers that's not hard math.
And people who are trying to sell are going to say to you, well, the average price for is, rather than saying, yeah, we had one that sold it for $50 million and that just threw the mean way off, but the mode is here.
People talk about math, but I mean these are numbers really. They're not the kind of mathematics that I'm talking about.
Mathematics isn't about calculus or solving some difficult equation. It's about problem solving, creative thinking.
Rather than mathematics, it's more logic. I'm very interested in the different logics that organize various fields of knowledge.
So in a way, mathematics depends on logic, insofar as it makes use of logic to prove theorems.
Logical reasoning, which is probably broader than strictly mathematical reasoning. I think that's inherent in human nature.
He was 6 years a prisoner in Vietnam. How he survived it, who can say? What was the math involved? What math did he have to do to survive?
We got a switch in the house. When it's off, there's nothing there, it says 0. You hit the switch one time, and then you got 1, which means it's the light is on.
Yeah.
So they take that, and that camera that you're using right now is all based upon electronics with zeros and ones.
The math I do useful to society? That's the most frequent question from non-math friends.
What do you mean use it? It's like saying, do you use gravity a lot?
All for peace, anti-war protests. Well, of course, that can be mathematically dealt with.
There are people who do methodology and people who apply methodology, and hopefully they're not completely separated.
In like really abstract math, we do it because of its applications to other math.
Most probably the field I'm in, the stuff, that topology stuff, is not really, you can't see it applicable to society.
I'm interested mainly, well, because I think it's beautiful. If you look at modern art is not necessarily about visual beauty, it's very much about intellectual beauty, a beautiful idea.
Yeah,
in the same way that we talk about ideas being beautiful, I think we can talk about ideas being beautiful in terms of in mathematics where it's just purely ideas.
I mean, I personally think intellectually I would identify more with an artist than a biologist.
You know, a lot of mathematicians talk about, you know, God created the integers, the rest is the work of man. I mean, there's a lot of different points of view of how people perceive what the math is that they're doing.
I think it's an attempt to apply as widely as we can imagine how to do the kinds of techniques that served us well when we were trying to fix toasters.
Truth, which is up there to be discovered and not to be invented. Objective truth, which is a measure of the world. Math is still the prime example of the possibility of such a thing.
I suddenly think it illuminates what mathematics is today if you have some idea of the history.
There's an incredible authority to how we think about numbers now, and yet there's absolutely nothing inevitable about that way of thinking about numbers.
I don't know too much about the history of mathematics, probably no more than anyone else who has a college education does.
The earliest math, if I'm not mistaken, is that of Babylonian math.
Babylonian is before Greek, right? And the Babylonians were very well known for being wonderful astronomers.
We are speaking about something like 1700 BC or something like that. Before you have the first clay tablets and numbers and all kinds of attempts to solve various practical problems.
Making very, very precise measurements of where the planets or where the heavenly bodies were.
Egyptian mathematics, which is a little bit later and less developed algebraically.
In Egypt, move those things in the pyramids, and look at what comparing that to the buildings today.
I guess that's one of the interesting things about looking back at the history of mathematics. You're like,
They didn't have variables.
I could have gotten my PhD so easily that I'd be famous. Like,
the way to construct right angles is to use a rope and divide it according to ABC, so that A squared plus B squared equals C squared.
I could figure this out. I mean, no, we only can figure it out because it's presented well now. But as a grad student, certainly I do lament the fact that I'm not infinitely older than I am.
I think math usually came from in Rome or Greek.
I've probably talked to a lot of people about the Greeks.
So we are speaking about 500 BC to about 300 AD.
They imagined geometry as what you could do with making circles and making lines. I mean, they used a compass to make circles and a ruler to make lines.
From there on, this is a period, is a golden age of Greek mathematics.
And they were a fish in water in ways they couldn't see.
As you know, the most noted Greek mathematicians of the time, or certainly some of them, were members of Plato's academy.
So part of that is just sort of historical accident that that it just happened that what developed into the modern collection of work of mathematics came mostly from the Western world.
The idea of doing it systematically from axioms and proving things, this is, if you want, it's a philosophically motivated idea that was implemented by mathematicians.
The Greek tradition, who were the ones who happened to most study first come up with the axiomatic formulation.
The whole body of beliefs, for example, our beliefs about the geometric structure of the world, can in fact be seen as depending on a much smaller number of basic fundamental beliefs.
The point is that Euclid gave us an axiomatic method, which is the method employed up to nowadays.
But there was certainly lots that was done in the Arabic and the Chinese world, and like they discovered many of the theorems that we use nowadays.
In Chinese math, I think there is a text from, if I'm not mistaken, 600 AD or something like this, called Math in 9 parts. Okay, and they have a lot of theorems there.
They didn't necessarily prove it in the rigorous way.
The proofs are not really valid, but the algorithms are.
But they did know a lot, and we do still use a lot, and it did contribute.
In particular, the Chinese remainder theorem, which is...
If I have, say, some number of people, like between 1 and 100, and I want to know how many people there are, I can get them to line up in rows of 3, and then I'll get a number of rows of 3, and then there'll be some numbers of people left over. And then get them to line up in rows of 5, and then you'll have some number of people, and then some people left over. And then line them up in rows of 7, and then again there'll be some number of people left over. And I can just count how many people are left over, and that will tell me how many people there were originally.
Has been a big tool in mathematical logic.
And I think maybe that's most, like China is kind of far away, so it didn't contribute necessarily, like at the time travel was very difficult and it didn't contribute so much to the Western development. But the Arabic mathematics definitely had some pretty obvious impacts.
The Arab mathematicians, they had a lot of algorithms, and actually the very notion of an algorithm, the very name algorithm comes from Al-Khwarizmi, who wrote profusely about this, giving all kinds of algorithms to solve algebraic problems.
Numbers that we use were developed by the Arabic mathematicians, and the names of many mathematical concepts come from Arabic. For instance, the name algebra comes from the name of a particular Arabic mathematician.
Indian, there's a lot of calculations, there's a lot of computing math.
They could do amazingly fine calculations. I mean, as far as I remember, they calculated pi to a lot of what were equivalent, they didn't quite have our decimals, but to the equivalent of a lot of decimal places.
We have also a first appreciation of some notion of probabilities, big numbers or something that can be chosen as random.
I mean, so the beauty of mathematics, we keep finding coherence.
One of the great mysteries and beauties of mathematics is that it is so interconnected.
You look at one problem and it looks completely different from another problem, but somehow exactly the same things come up.
I don't really know why. I mean, that something invented for one purpose happens to be useful for some completely different purpose.
And that is just an amazing thing. That's one of the fascinating, if you see it, it's one of the fascinating things about mathematics.
I mean, that's maybe what leads people to believe that there really is something there, is that these structures that you find happen to be useful more than once.
For example, you have the integers. I mean, nothing could be sort of more obvious than the whole numbers, 1, 2, 3, 4, and yet they have these most amazing properties that just the kinds of symmetries that they have just crop up in many other seeming to be completely unrelated areas.
Suggesting that there really is some sort of kernel, some crystal of pre-existing stuff that we're just discovering and coming at it from different directions.
In some sense, it's answering that age-old question of like trying to understand the world around us and trying to model the world around us. But in another sense, it's like a giant game that people are playing. And it's where at times you get to make up your own rules, and as long as your rules match with the rules created by everybody else before you, it's legal.
So I as far as I understand, if a logician actually looked at mathematics, they would think we were incredibly illogical and missing out all kinds of important things.
Now, you may ask, do mathematicians use the same kind of logic that logicians develop? Well, that's an interesting question.
Concept of logic, a sort of functional concept of logic, that's the working definition that works for mathematics.
To some extent, the answer is yes.
In mathematics, what I think we do is we look at a situation and try and understand it in whatever way we can, and we make definitions, we try and create words to describe it, and then we try and prove theorems which explain the relationships between certain things, certain ideas that we've had. And the proofs are sort of what hold everything together, because the proofs are meant to show that one concept is really logically related to another concept.
Like there are many things that sort of seem true and like that you come up with these ideas, and one thing that you discover when you actually go and really start learning mathematics is that it's very easy to fool yourself. Like it's easy to believe that something might be true, when in fact there are some special cases where it doesn't quite work, or maybe it's true only for numbers up to 10 million, and after that it's false. So there's this idea of proving it, like coming up with an explanation that is guaranteed to be right, that it's always going to be true.
I mean, if you prove something and it's contrary to what you might have thought, I mean, it's still true.
Mm-hmm.
So, you know, you learn to live with that.
Proof is a kind of reproducible experiment where a proof is really just another explanation that another person understands.
So let me give you an example of what I mean when I talk about, you know, the proof that a certain conclusion follows from certain premises as a matter of logical necessity. Now, this is by itself a complicated story, but I'm going to illustrate it with a picture. So consider a simple argument, a simple piece of reasoning. All humans are animals. That's one premise. Second premise, all animals are mortal. Therefore, conclusion, what? All humans are mortal. That's in fact a syllogism. And so I'm using an example that goes back to Aristotle. So there are three claims, two premises, all humans are animals, and we can represent the world as described by this premise as follows. This is the set of all humans. The first premise says all humans are animals, so it says that this set is included in the set of all animals. So these are the humans, these are the animals, all humans are animals. There is no human outside. The second premise says all animals are mortal, so it says that the set of animals is itself included in a larger set, the set of mortal things. You cannot find an animal outside that larger class of mortal things. That's the second premise. So we have now depicted the world as it is according to the premises. Whether this is the actual world is irrelevant. The premises say that this is how the world is. And now the argument says, therefore, all humans are mortal. And look, that's exactly right. All humans are in here, and that class is included in the class of mortal things. So in a way, I don't have to do anything to depict the conclusion. It's already on the board. That's to say that the conclusion follows from the premises. It comes for free. Once you accept the premises, once you take this to be a good picture of the world, the conclusion is already included.
What I'd like to do is explain one of the arguments that astounded the Greeks. I mean, it's a traditional argument from the time of Pythagoras, and it was just something that they couldn't quite understand, because for them, numbers were whole numbers, or possibly fractions, and so they were very happy with numbers like root 2, or more generally you'd say p over q, where p is some, and q are whole numbers. And then they found, you see, when they do geometry, they find there's something called root 2, because when you look at a triangle with sides of length 1 and hypotenuse there, Pythagoras' theorem tells you that root 2 squared, whatever side this is 1 plus 1, which is 2. And so we have this number. This is a number, because for them also, if you could construct a length, its length would be a number. So why is root 2? So the theorem is that root 2 is a new kind of number, and it's not equal to something of the form p over q. And the proof is this. You suppose it is. And then what you do, because it's a fraction, you suppose that at most one of p and q are even. Okay, because if they were both even, you could divide out by 2, and then you eventually get something where at least one of them is odd. So then if this is true, then you square and you get that 2 is equal to p squared over q squared. And so you rewrite that and say, okay, p squared is equal to 2q squared. And so p squared is even. And then that tells you that p is even. And so what you do now is you, I'll have to go up here, you write p as twice some other number. So now k is a whole number. And you go back to this equation here, and you substitute for p. So you get 2k squared is equal to 2q squared. but this is 2k all squared, so that's 4k squared being 2q squared. And so now you cancel the 2, and you get that 2 of k squared is q squared. Therefore, q squared is even, and therefore q is even. And you see this is a contradiction, because we assumed at the beginning that at most one of them is even, and we've actually concluded that p is even and that q is even. So that's impossible. That's what the Greeks, that's not possible to have both this statement true and those statements true. And since our reasoning is true, it means that our hypothesis must have been false. So this hypothesis is false. And so there's your proof. It's what's called a proof by contradiction.
I'm going to give you a really simple example of a counting proof in like combinatorics. So this is using the pigeonhole principle.
If you want to use the board too, that's fine.
Oh,
Unless you can do it verbally.
Yes,
you can do it verbally.
This is beyond easy.
Go for it.
So the pigeonhole principle is the idea that if you have 100 pigeons and 99 pigeonholes, and you say to them, I'm going to turn around and y'all going to get down in a hole. And I don't care how you do so, but when I turn around, I'm not going to see any pigeons anymore. When you turn around, you know that since there were 100 pigeons and 99 holes, that somewhere there's a hole with 2 pigeons. Okay? Now, in reality, there may be one hole with 99 pigeons, there may be 2 holes with 48 and one hiding someplace else, but this is what bothers some people, the fact that I can't show you where the hole with multiple pigeons is. But sometimes it's actually really important just to know that there is one out there, because then you can go looking for it.
And so that's what we have. I mean, physicists have experiment, for example, that might test their ideas, but we have proofs that test our ideas.
I mean, you ask me things like, what do you feel when you've just made a proof? And I think, great, have something to show my advisor. if I work more, then maybe after finishing after like getting rid of all the mistakes, I might be able to publish a paper.
Do you ever listen to Bloomberg or CNN? Do you ever hear how many people are sure of very opposite things?
Proof is a formalization, an indicator, like many indicators I used, in economics and
You can pull out certain things and come to certain conclusions, or you can pull out other things and come to other conclusions.
I'm precisely interested in the possibility that that particular closure that a formalization represents is excluding things that are either there, they have always been there, but they have not been factored into that proof, or that there are new things that cannot be captured by that particular closure, that particular indicator, that particular proof.
Is it malicious? No, I think these people are doing their best. It depends. There's so much information. It depends on what you wish to use, and mostly that's determined by the conclusion you want to reach.
All of this raises really deep questions.
People get in trouble when they take as true things that they've been told on good authority are true, but they don't understand the way it works.
What kinds of objects are these numbers? If they're abstract entities, if they're non-physical, abstract, platonic entities, how is it that we could have any kind of access to them at all? How is it that we could learn anything about them? We don't interact with them physically, so on and so forth. These are really good questions. These are really deep questions.
So there's a tendency for mathematicians to want to understand, at one point, the proofs of what they use.
And the answer is going to be something like, it has to do with my experience with toasters.
Well, I think mathematics, I think that people's brains have developed in interaction with the world, and therefore the kinds of ideas that we have often are sort of consonant with what happens in the world.
You say the toaster isn't working because it's sad, okay? And you try to take an approach based on that. That turns out to be much less successful than saying, I want to look at the internal mechanism, I want to see what's banging into what and what's not connected to what, and my idea is that's going to be more useful for getting the toaster to work again.
That is right. I mean, so, but I would argue that that you need empirical experience to understand the concepts.
Yes.
I don't think the concepts themselves, once they are understood, leave you any place to maneuver them.
All the stuff that we do and the way we learn, it evolves and it comes from the creator. So zeros and ones, math.
I don't think it's my experience of living in the world that creates this. I think it's just that the way the human brain is made, which is built up of the experience of life over however many millions of years, has created a brain that sort of works in a particular way.
There are basic mathematical structures that I don't want to speculate how we get them. It's part of our genetic endowment or our genetic endowment working in this world, but the intuitions are so strong that I must take them as basic.
I think what God has created, he then puts the formulas and we then learn the formulas of what has already been created.
In that sense, I'd say that largely mathematics is about understanding the world. And there's a sense to which all these things are out there to be described. And while today's version may be mathematically modeling the effects of an earthquake or the synapses between our nerve cells and how much firing goes off, that may be on a much quote-unquote higher level than understanding that zero exists, but we're still trying to figure out what's going on and what it all means.
Like, it's all interconnected. Like, the tools from, I'm going to use some technical terms, but just different areas of math. The tools from algebraic geometry happen to apply to studying topology.
And a lot of the times, you find this connection that our basis is in reality, but you don't want to necessarily, want to build up off of this basic reality. You want to, I think, a lot of times you come back down.
You study the topology of various systems, and then that happens to explain dynamics like the behavior of solitons. Like when you blow a smoke ring, why do the smoke rings persist? That's related to some topological behavior.
You don't not only want to build up the layers of abstraction, you also want to see if you can come back down either to reality itself or to something else that has been discovered.
It's a little bit of which came first, the chicken or the egg, when you talk about like physics and math. Sometimes mathematicians come up with stuff and it seems like freakish, who needs this? And then 20 years later someone says, oh wait, this perfectly explains blah blah blah. And other times a physicist comes up with a question and says, well, I don't know what I'm doing with this, maybe there's some math that can help.
The Big Bang was like an old flash bulb in a picture, and the flash is still resonating in the universe. You look various ways and see how strong the residue of that flash bulb is, and it gives you kind of an idea how far things are different ways. And people are trying to fit that together to say, what's the geometry of the universe?
It's a little bit hard to imagine how the three-dimensional universe might be connected because we don't have a place to stand outside the universe and look at it. So it's a little bit easier to imagine how a two-dimensional universe might be connected. So you might imagine some creature living in the plane. So some stick figure living in the plane, and can walk around in the plane. But this is not it's stuck in the plane. He can't get out of the plane. So the easiest thing to imagine is that it's this blackboard extends out forever, and it's just a single body that you could go off and explore. But there are other possibilities too. This fellow might be living on the surface of a ball, where if he goes far enough in one direction, he eventually comes back on himself from another direction. Or there might be a more complicated surface, like say the surface of a donut, which is a little bit more complicated, or say the surface of an object like this, which where there are various different ways where you could walk in one direction and come back on yourself, either around here or maybe around here, a whole bunch of different ones. I mean, this is a reasonably complicated surface.
Something that happened in the 20th century, particularly with the advent of quantum mechanics, was an idea became very widespread among physicists that that the kind of confidence we had formerly placed in these techniques was reaching its limits.
It's always going to be a beginning. Math, we're going to come up with different things. It's always going to evolve. God is going to give us more. He's going to let us have that more information that we're going to wind up evolving.
It's uncomfortable to be uncertain or feel stupid or not know what you're doing or wonder what's going on in a situation. And a lot of people, are forced through that discomfort when they're getting their education. But then, they like, there's a certain security in being good at what you do and mastering a small domain, and then not being forced into a different domain where you feel really out of sorts and dumb.
Very much of the thrust of my own work over the past 20 years has been directed at, and I know that this is something that I didn't manage to, this is a view that I didn't manage to convince you of in the course of the quantum mechanics course. But all I can say is what looks right to me. And what looks right to me now is that these conclusions about the collapse of mechanism in the face of quantum mechanics turned out to be premature. Okay? It turns out that if you work a little harder than those guys did, and you insist on thinking a little more clearly than those guys did, reasonably mechanistic sorts of pictures of what's going on, even in the case of quantum mechanics, become available as well.
Thinking about this kind of question, it is actually natural to think about time as being an extra dimension. And this is all like Einstein really convincingly showed that time and space are kind of intricately linked up with each other, and that you can rotate one into the other in a kind of funny way. So really there are 4 directions that we know about. And well, there are some theories that there might well be extra dimensions that are kind of curled up too small for us to know about.
One shouldn't say that too glibly. There are surprises there. There is this phenomenon of non-locality in quantum mechanics, of things being able to affect one another without touching one another, and moreover, without touching anything that touches one another, and without touching anything that touches anything that touches the other, and blah, 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 blah. This is a real shock to our toaster-trained intuitions about what mechanical objects behave like. But nonetheless, it looks like we can explicitly write down a set of laws, we can explicitly develop a clear physical picture of what's going on with these systems in the way that people involved with quantum mechanics throughout most of the 20th century thought that we couldn't.
People have been thinking for like so long that eventually they would have gotten to this point. I'm sure 100 years from now, somebody will have an even more abstract theory about something completely different. Something to do with math, like vegetables or something.
I mean, I think there's a certain humility in paying attention to history. Because, I mean, when you realize that everyone before us didn't really have a complete clue what was going on, but they thought they did, then, well, gee, I mean, it'd be pretty arrogant not to draw the conclusion that we also don't really have a clue what's going on, we just think we do.
The issue of quantum mechanics was a particularly interesting issue because this was the first occasion. There had been for many years critiques of this mechanistic picture of the world, as it were, from the outside of physics, okay? That there were all sorts of mental phenomena, all sorts of ideas about free will, all sorts of ideas about meaning, so on and so forth, that people insisted again and again no mechanistic account of the world could do justice to. What was unique about quantum mechanics is that it looked like the mechanistic project was failing from the inside, not from the outside. That is, it looked here like the mechanistic project was going to fail not just for ideas or for consciousness or for meaning, but for rocks, okay? Even rocks, it turned out, weren't going to be thoroughly mechanistic objects.
Where are you going to go without numbers, without calculations, without formulae, without equations? I don't know.
If somebody says to me, and I have the impression that this is part of what you're interested in, if somebody says to me, why do you think this way vis-a-vis, say, economic policy in the third world?
Which is what econometrics is about. We observe, we collect data, and then we process it using statistical methods.
Here's an important decision that we want to make. How should we go about doing it? About policy, about economics?
What has been the result of a policy intervention? So if Congress votes a plan to solve the mortgage crisis, how can we evaluate later, based on data that we collect, how successful this plan has been?
There is this kind of tug. Look, there are these techniques that work well for fixing toasters.
Mathematical reasoning encompassed in a relatively simple mathematical structure to throw light on important and complicated historical processes.
There are these techniques which, in the cases where we can clearly and vividly and quickly see the result of this kind of reasoning as opposed to the result of that kind of reasoning, there are certain techniques of thought that prove successful.
Two philosophers get in an argument, and they could argue for the rest of time and never agree. I mean, two mathematicians get in an argument, and you know, they might argue for a really long time, but one of them's incorrect. And in every math argument I've ever been in or witnessed, someone realizes that they're wrong and says, "Oh, you're right."
Here's what's impressive about the toaster case. What's impressive about the toaster case is no matter what their initial prejudice is, everybody eventually agrees on the right way to build a toaster.
I mean, the way we do math, it's all based on like, it's all about writing down a set of rules and following those rules.
We have to try and make things logical because that's the only way we know how to make them coherent.
We know that you can't establish essential truths. The most one can do in scientific reasoning, even in much more developed sciences like physics, is to make predictions that are consistent with the observed phenomena. To that extent, I think in a more humble sort of way, economics can also rely on this sort of test.
I think of master categories as enormously powerful, and they're partly powerful because they do explain. And this is also the notion of an established proof. It explains.
This method enables one to concentrate on the relationships between the essential variables. So rather than, if you just make a historical account, you know what happened, but you don't know, you know, what were the necessary connections between the different events, right?
But precisely because they are so powerful and so clarifying, I also argue that they blind us.
Maybe. I mean, I guess the reason why it's possible to reach a consensus is because, like, the discipline is restricted to things that can be proven via these means, you know,
Mm-hmm.
and if something's outside the domain of those proof capabilities, it doesn't count as mathematics. And I mean, so in that way, like, we are restricting it for the sake of this decidability.
Mm-hmm.
But I mean, it so happens that didn't, like, it left us with plenty of richness.
I don't know what else to depend on. And if it's a case where, say, people's lives are at stake or people's welfares are at stake, you want to be in a position to have a story to tell yourself about why you chose this way of approaching the problem as opposed to that one.
We're trying to make the most of all the information we have.
This idea that fixing a bad economy, it would be great if fixing a bad economy was like fixing a toaster.
Global medical problems, highly mathematical. I mean, we had actually men who are math professors. They were in the program, they were lecturing to us on global statistics and the gaps in treatment.
So there is information that is really a priori. I'm not going to get too philosophical, but that is based on theory, on introspection. There might be information we use to decide what would be a good policy, for instance, that is based on our knowledge of history, of what has happened in the past. And people constantly refer to, for instance, the Tax Reform Act of '86 in the United States, or maybe the Kennedy tax cuts, or maybe things that happened even way before that in the history of America.
Now, of course, the question arises is how do you know that you're right? You can't be sure that you're right. It's impossible to do that. But the check on whether you're right or not is if you manipulate your model and get a prediction out of it. Let's say, and you say that X, factor X will have a certain, an increase in X will increase Y or Z. If that's the prediction of the model, and then you turn to history and you find, yes, X did increase and Y and Z did increase in the manner that your model predicted, then at least you can say that your model is consistent with what actually happened.
I can't see what else to be yearning for, okay? Because once again, these are serious questions, okay? These are questions on which people's lives and welfare depend, and you want to be in a position to be able to explain to yourself while you're going to sleep at night, and to be able to explain to the victims of whatever policy you've come up with what it was that led you to arriving at this policy.
Years ago, in a Washington, D.C. school where I taught, it was adult education, but you can see. We're dealing with t-tests, we're dealing with just basic statistical matters, you know.
Yeah, I can see. Is that you?
Okay, that's me.
Oh, yeah?
Yeah. That's just one picture. Here's another. I got pictures from all. I've taught in 3 foreign countries, and yeah.
It's really sad math is the subject in school that you're allowed to hate. And it's almost cool to hate math. And I always found that kind of strange and sad, and I think that if more people have positive experiences with it, maybe that cultural aspect can change.
And you'll find a lot of mathematics is
relationship. Mathematics is relationships. Relationships always exist.
A lot of mathematics is looking at just trying to build those connections.